In this example, we have an inverse relationship between the water temperature of the Pacific Ocean and the depth of the water. We would anticipate that as the depth of the water increases, the temperature would decrease, and vice versa. We know that as an inverse relationship, we're going to follow our inverse variation equation, y equals k over x. At a depth of 1,000 meters, we have a temperature of 4.4 degrees. When you start to get into more complicated variations, it's probably not a bad idea to code this variation with each variable, in the meaning of each variable. We know that k is the constant of variation. I'm not worried about that. But we know that the x is going to represent the depth. That's going to be the independent variable in this situation. And we know that y is going to represent the temperature of the water. If you're having a hard time remembering who goes where, it's not a bad, and this can even work for direct variations and our future variations. It's not a bad idea to start labeling them, especially as you write the equation generically with y equals k over x, and then maybe even switch it to temperature equals k over depth, and you start making the substitutions that way. 4.4 degrees is associated with a depth of 1,000 meters. Multiplying and determining k, we get that k is 4,400, meaning our actual inverse relationship is 4,400 over the depth. We are asked about a depth of 5,000 meters. So we'll put that 5,000 underneath the 4,400. We divide the two of them, and we get a temperature in Celsius that is less than 1 degree. So again, with an inverse variation, we're starting with our generic equation. This one, it's a little bit tougher to keep track of who belongs where, so a variable substitution probably isn't a bad idea. Get that representation correct, and then just sub in as we did with the direct variation, figure out what k is, and then work your way down on your unknown variable.